Hello, hi, welcome back. So I am 𝐶𝐞𝐞𝐝 Ghosh, a senior CPU design verification engineer, and I have been working in Synopsys for more than 1 year. And uh, previous to this, I have been working in Intel for over 2 years as a CPU design verification engineer. And before that, I did my MTech from IIT Kanpur, and I was a topper there. So yeah, I have a uh, like fascination for learning. Okay, I have a deep passion for VLSI industry. And so I'll be continuing here with the HDL bit problem solving. Give me a minute. So I'll be continuing the HDL bit problem solving from wherever we left yesterday in the last video. Okay. So as always, uh, try to pause the video and uh, solve the problem yourself. So this is a problem walkthrough. So you can solve the problem yourself. And if you cannot solve it, or if you want to know a different approach, you can see my solution. Okay, how I solve it. And then if you face any problem in understanding what I am explaining, or the way I am solving, if you are not able to understand, please let me know in the comment section. I'll make a detailed video if needed, or I'll try to explain in the comment section. Okay. If you have a better approach or a different approach, feel free to share in the comments and have a healthy discussion in the comment section. Okay, so let's start. I'll share the screen and we will get going. So I'm currently sharing my screen. Okay, so let's start. So we will go to problem set, browse problem set, and then this was the problem we were about to solve. So you are provided with a BCD, one digit adder named BCD full add, that adds two BCD digits and carry in and produces a sum and carry out. So we are provided with a BCD one digit adder. So it's a one digit BCD add named BCD full add that adds two BCD digits and carry in and produces a sum and carry out. Okay, where is it? Named BCD full add. Okay, the name is given here, BCD full add, that adds two BCD digits, and carry in and produces a sum and carry out. Okay. This is what they have given. Good. So it's like 3 down to 0. Good. It's not 400 down to 0, 300 down to 0. So it's like it's a 4-bit thing, and I want to make a 100-digit BCD ripple carry adder. Instantiate 100 copies of this to create a 100-digit BCD ripple carry adder. Your adder should add two 100-digit BCD numbers packed into 400 bit vectors and a carry in to produce 100. Okay, good. So what we need to do is we need to have a always at the rate start begin end, and then we need to write the logic for instantiating hundreds of this uh, BCD thing. Okay, so we will need a wire as well. So we need a wire. So we need a 400 down to 0. Okay, so it's a 401 bit wire. So one of them will be C in, another one will be C out. Okay, and what I will do here is uh, and then we have N. Let's name the wire as not N. It's like C carry out. Okay, so this is carry wire, not carry out, carry. Okay, and what we will do here is inside always we will say carry equal to carry of 0. Actually, we don't need a 400 down to 0. We only need 100 down to 0 actually. Because each and every adder, each and every BCD adder will consist of 4 bits. So it's like 4 bit. One BCD adder is 4 bit. So if I just take a paint, so here we have a kind of 100 so this adds 399 down to 0, which is A. Okay, which is A, and it adds a B, which is again 399 down to 0, 400 bits. But there are B, C, D, sorry, 4-bit adders, 4-bit. So it's like here we have A 3 down to 0 and B 3 down to 0. Okay. So this is how each and every uh, of the BCD address will be connected, and there will be like 4 bits that are going here, but one carry in, one carry out, 1 bit carry in, 1 bit carry out. Okay, so this is how things will go. So we have okay 100 of those adders, and we have at input 1, and then each of those 100 adders will have one output. So it's like 100 carry out plus 1 carry in. So we need total 101 wires for carry. Okay, if I want to replicate the code in that sense. Okay, so here we have 101 wires, 100 down to 0, 101 wires. So carry of 0 is C in, carry of 0 we are calling it as C in. Okay, and then what we are doing is we are saying carry of 100. Okay, carry of 100 equal to C out. Sorry, we shouldn't do like that. we should do carry out equal to carry of 100. Oh, we don't need to do like this. What we need to do is carry of 0 equal to 𝐶in. We'll assign it. Or we don't need a reg wire. We can just use a reg. Then we don't need to do this kind of assignments. Okay. Here we will have carry of 0 equal to 𝐶in. So carry of 0 will have the value 𝐶in. And then what we will have is 𝐶in is okay, not an issue. Carry out is uh, okay, not an issue. It need not be a register. I'll just put a wire here. Okay, and after that, what we will do is we will write the for loop. We'll write the for loop. So we are taking carry in carry of 0, carry in carry of 0, so that we can write everything in for loop. For int I equal to 0, I less than 100. Okay, I equal to I plus 1, and then we have a begin end. Okay. Now what we will write here is the logic. Okay. Basically, we will call this module BCD full add. And then we will write A, which is A. Okay. And then we will write, we will connect it in such a way that A of 0, 3 down to 0. Okay. Like I into 4 plus 3. So let's say when it's I equal to 0, 0 into 4 plus 3 down to I into 4. Okay. So what happens here is we are saying I into 4. So 0 into 4 plus 3. So it's like 3 down to 0. Okay. 3 down to 0. In the next time, it will be like 7, 1 into 4, 4 plus 3, 7 down to 4. Okay. That way. So this is A. Now we will do the same with B. Okay. And then And then what we will do is we have 𝐶𝑖𝑛, which is carry of I, carry of I. So initially input will come as carry of 0, which is 𝐶𝑖𝑛. Okay. And then we have carry out, which will be the next one, carry of I plus 1. And then we will have sum of, in the sum also we will have the same as A and B. So we will have sum of, okay, this. So after this for loop, what we will do is Cout equal to, we will write Cout equal to carry of 100. Okay. So this is done just so that I don't have to write this for 𝐶𝑖𝑛 or Cout separately. I can just say carry of I plus 1, and carry of 0 gets the value of 𝐶𝑖𝑛, and carry out gets carry of 100. Okay. And then we are returning. Okay. So this is the code. Okay. We have wire here. Uh, wire. What we can do is assign. Give me a minute. I'm a bit thinking like carry should be wire or register. So we are making it wire here. So carry in gets 𝐶𝑖𝑛, which will not be possible in this case. Okay. It has to be a register. And carry out should be assigned as carry of 100, because carry out is a wire. This carry out is a wire. So it should be assigned to carry of 100 all the time. Okay. Carry out is a wire. So it should be assigned to carry of 0 all the time. And this carry should be a register because it needs to hold the value. It needs to hold the value. Carry of 0 needs to hold the value till the time it changes, till the time these inputs change. Okay. Carry should be register, but carry out will be a wire. So carry out, we don't need to assign it here. Okay. Carry of 0. So carry is a register. It gets the value of 𝐶𝑖𝑛 whenever there's a change, and it calculates. And carry out always have carry of 0. Okay. Sorry, carry of 100. Carry out always have carry of 100. So, okay. Now that makes sense. Let's submit and see what happens. Okay. Is not a task or void function file. Let me see. It says BCD full add, which is given the same name, BCD full add, is not a task or void function file. Line number 12. Okay. It's saying we should not be writing like this. It says I is not a constant. Did not compile. Not a task or void function file. I is not a constant. I is a variable. Yes, it is how I made it to be. Assign carry out. Carry out is a var equal to carry of 100. So let's remove these brackets. Maybe this is the issue. Not exactly sure why this is the case. There's a another way we can solve this using genvar. Okay, we can solve this using genvar, but I don't want to solve it using genvar here. Okay, so I should not be taking var here because then the carry things will not be taken into account. We are actually making a connection here. In that case, we don't need to write this as reg, we can write this as wire. We are making a connection, so it will be continuously driven. Okay. For structural case, it can work like that. And here we can say assign carry out equal to, we can say assign carry of 0 equal to 𝐶𝑖𝑛. We can do it like this also. Okay, we can say assign, if I make it wire, we have to assign carry of 0 equal to 𝐶𝑖𝑛, and then because we are making a structural connection, this should work. Let me submit and see what happens. So these are wires now. Let me see what hint they are giving. An instance array or generate statement would be useful. Instance array or generate statement. Oh, so they are in fact asking us to use genware. Then it's best because that is what I was planning to use. I was thinking genware would not work here. Genware of I, and then we just need to copy the same thing. Okay, we just need to copy the same thing here. We don't need this always begin. What genware does is, it creates multiple copies of this. So basically in the code, what it will do is it will replace this loop with this instruction getting repeated multiple times. Before compilation, it will do this. And after that, those 100 lines of code, this getting 100 times replicated, that will be compiled. So there's a difference between for loop execution and genware implementation. So they are saying that okay, generate statement, which is actually a genware. Okay. So I am creating here the genware of I have to see how to write the genware. How to write genware in system Verilog. But actually, I'm thinking about the semicolon here. We don't need a translation here, anyways. Genware of I. See, genware of I. There's a semicolon, and they have also written generate and generate, which is optional, which is not needed, but we can write. Okay, we can write genware of I semicolon. We have a semicolon here, and then generate and then generate. That is what we can use. Genware of I, we need a semicolon. Actually, for semicolon only, I was checking. Generate, after that we don't have a begin end. Okay. So we can write end generate. Okay. Uh, yeah, we can just put a uh, this kind of tab. Now we can just submit this file and see what happens, because we have done the required assignments. Carry in is assigned to carry of 0, carry of 100 is assigned to C out, and now this code should be replicated around 100 times. This block requires a name. This block, oh, I forgot to give a name for it. So without a name, it can't replicate. Okay. So in line number 12, okay, it says, I don't think there should be a name in other places. We just need a name here. We just need a name here, which is uh, BCD4 add. Okay. So let's take that as the name. For block also they are asking for a name. For this block, they're asking for a name. So let's give a name like this. And then see, let's see what happens. Okay, I never knew that this level is so important or needed. Actually, I have used Genware in model sim. This is not needed, to be honest. So they are somehow asking, no, 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 give a level, give a level. I don't know why. Uh, it doesn't make much sense to me. Even if we don't give any label, we should be good to go. So generate and then generate, and they are asking for a loop label and also a name. Okay, here for the BCD full adder. So it's like an instance name. When I use generate, what it does is it creates some kind of this dot I, so, or underscore of I. Okay, I means here like 0, 1, 2, 3. So BCD4 add underscore 1 underscore 2 underscore 3. This kind of thing it creates in the background. So that's why they want a name for it. So, okay, at least we have a working code. Okay, great. Uh, okay, you can check out this code, and I've explained things like carry. What we are doing is we are creating as wire, and that is why we are assigning carry of 0 equal to C in. And this carry out is not a register because we haven't written anything register or something. So carry out also we are assigning as carry of 100. So we are not saying it is a register. We are treating it as a wire. And then this is actually a structural connection. Structural what it is called? Structural code. Okay. So we are giving 4 digit A, 4 digit B, and carry of I, which is in the first time iteration it will be seen. In the last iteration, this carry of 100 will be given back to C out, and some will be directly given back via the port connection to the test bench. Okay, so yeah, it's a success because we gave this module instance name and a label. I don't know why this is important, but uh, see, for cross module reference, this is helpful. Otherwise, we cannot use cross module reference. But here, I don't know why they are asking for this label. We should not need this label until and unless we use cross module reference concept. Okay. So until and unless we are asking for any, you know, of the instances, so there will be 100 instances, unless and until we are searching for any instance and doing something with it. Okay, specifically, till that time, this level should not be important. But okay, okay, so because there's a single name only. Okay, there's no point of confusion. We can just say top module and then this BCD4 add underscore I, which will be the replicated code. Okay, so this should not be needed, but okay, they have some uh, code which says okay, these all things are needed, basic checks without which it will not run properly. So maybe this is the case only for HDL bits because I didn't saw this in uh, model sim and even synopsis VCS. So okay, it's okay. It's good that we understand the problem or the error message and we can change things accordingly. Okay. So before this we were doing Verilog language, this generate for loop 100-digit BCD adder. Now we went on to the next problem, which is the circuits thing. So we came out of Verilog language, we came into circuits, combinational logic, basic gates. So we are now dealing with wires. So it says implement the following circuit. Here we have a in, here we have out, and there's a wire connecting both the things. So how to write? So this will be very simple now. So we will say assign out equal to in. Okay. What we are doing is assigning out, sorry, assigning input to output. So it's like we are connecting input to the output. We are assigning input to output. Okay. Okay. Yeah, very simple one. So after we have solved this kind of questions, like the adder kind of questions, this is very simple. So it says out should be connected to ground. So what we will say is assign out equal to 1 tick B0. Assign out equal to 1 tick B0. So out have constantly this value, constantly. Okay. So yeah, let's submit. Here out is a wire. So we are using assign statement for continuous connection. It's a success. And it says output pins are stuck at VCC or ground, which is what we want. Output is connected to ground. Okay. So, okay, let's go to the next problem because we saw previously adder kind of things. Now these will be very easy. When we go to K map and all, the things will be a bit interesting. Okay. So I don't know what we have with sequential logic. We have multiple things building larger circuits. Good. Okay, let's go to NOR gate. Now what do we have here? We have a NOR gate. Basically output is the NOR of input 1 and input 2. So we will say assign out equal to NOR. NOR means not of OR. OR means input 1 or input 2. So we are doing an OR operation, which is actually a bitwise OR operation. Although we have 1 bits, we can just use uh, this OR, which is checking whether the output is true or false. Here doing bitwise OR operation, and then we are negating it to get the output. Okay, we need a semicolon here, and then we can submit. Okay. We should use uh, these, or it's like arithmetic or, not logical or, and this is arithmetic not. It's like complement. Okay, we should use this so that we can also work with multiple bits. So if input 1 is a 10-bit vector, input 2 is a 10-bit vector, and output is a 10-bit vector, output will have 10-bit value if I do this. Okay, if I use logical OR, which is this double pipe symbol, or if I use a NOT, which is a logical not, it's not like complement, it's like logical not. Exclamation mark is logical not. It's not a complement operator, it's a not operator. In that case, the output will be a 1-bit vector. So if I want that kind of a logic, then yes. Otherwise, we should use complement. Okay. So yeah, it's a success. So let's move on to the next problem. Here it wants an AND of input 1 and not of input 2. So what we do here is we say assign out equal to input 1 in1 and not of complement of input 2. Okay. Input 1 and complement of input 2. We can just give spaces, it looks good, and we can submit. Okay, I gave semicolon, so good. Yeah, it's a success as usual. Great. uh, and then we have 2 gates. So what we do here is we have an intermediate wire here which doesn't have a name. What we will do here is we will say wire n1, let's say, or wire n, because we only have one. Then what we can do is we can say assign n equal to XNOR. So it's like complement of XOR. So we say input 1 XOR input 2. We do XOR and then we do complement, and we take this as input, n as input, assign. Okay, out equal to n XOR input 3. Okay, n XOR input 3. Okay, submit. So yeah, it's a correct logic, and you see a success here. So okay, let's move on to the next problem. We have more logic gates here, which is like same thing again and again. So what we will do is we'll try to uh, okay, let's copy this. Okay, we have here written everything written here. So we take this, copy, and then we write this here. and okay. So assign this equal to we have a, it'll get complicated. Say a out and b. Okay. Now let's copy this. Let's copy this. Okay. And here we have OR. Here we have XOR. Here we have NAND. So and then not of AND. Okay. And then we have NOR. So we have OR and then not of OR, NOR. And then we have XNOR, which is XOR. And then we have not of XOR. And then we have A not B. So A and not of B. Okay. So brackets are not must, but it's a good habit to put brackets. A not B. Okay. So it says out and is A and B, A or B, X or B, A and B, A nor B, X nor B. Okay, very good. This is A and not of B. So I did A and not of B. Good. With the name only I understood. Anyways. Uh, okay. Seems good to go. Let's submit. We have proper names. Nothing should be wrong. Status success. Okay. A very simple problem like the ones we are solving here. So let's move on to the next problem. Now we will have some uh, like interesting problems. Okay. The 7400 series integrated circuits are a series of digital chips with a few gates each. So this is a chip. It's like 7400 chip. Okay. It's a like 4 input NAND gate. Okay. Now it says there are 1, 2, 3, 4, 5, 6, 7 inputs this side, 7 inputs this side. It's a dual inline package, DIP, dual inline package, uh, IC, whose name is 7400. Okay. So if you search 7400 IC, okay. And then if you see images, it's a 7400. So it looks like this. Okay. It looks like this. I am not sure exactly what should be the circuit diagram because I see here like there are 4 NAND gates, uh, but probably okay. It doesn't matter because they have given this circuit. They are requesting to implement this circuit, but it looks something like this. You know, some 7 inputs this side, 7 input that side. I mean 7 pins this side, 7 pin that side. Okay, it looks yeah something kind of like this. Anyways, whatever the circuit they have said like implement this, so we should implement this only because this is what they will check. So it's a AND gate where P1Y is the output and P1A, B, C, D are inputs. Okay. Okay. P1Y is the output. P1y. We will say assign P1y equal to not of and. It's like NAND. P1 A B C D. Okay, A B C D. And P2A is P2A, P2B, P2C, and P2D. P1y, P2y. Okay. Not of and. Not of and. Okay. So good. Uh, let's see what is there. Let's submit. Okay. It's a pretty easy and straightforward problem. Okay, great. It's a success. If the naming is correct, like P1A, P1B, P1C, P1D, and if you don't mess up the naming and all, it's a pretty straightforward problem. So let's move on to the next problem. Okay, so truth tables. So what they are saying is implement this truth table. Implement this truth table. So what I can see here is okay. Let's not put much of our head into it. X3, X2, X1, and F. Okay, so let's go through. Did we have anything to explain in this circuit? Okay, it was saying that okay, it's a chip of 4-input NAND gate, create a module. Okay, anyways, so truth table we will explain. So this is the truth table which we need to implement here in this problem. Okay, in the previous exercises, we used simple logic gates and combination of several logic gates. We used simple logic gates and combination of several logic gates. Okay. So these circuits are examples of combinational circuits. These circuits are example of combinational circuit. Okay. Combinational means outputs of a circuit is a function in the mathematics sense of only its inputs. So output is a function of its inputs in a combinational circuit. Okay. This means that for any given input value, this means for any given input value, there is only one possible output value. Okay. So it the output doesn't depend on any clock or it doesn't have any memory. If I give the same input, I get the same output every time, each and every time. Okay. Thus, one way to describe the behavior of a combinational function is to explicitly list what the output should be for every possible value of the inputs. Okay. One way to describe the behavior of a combinational function is to explicitly list what the output should be for every possible value of inputs. So for every input combination, what should be the output? If I can write this, so I know how the circuit works. Okay. That is called a truth table, which tells us the true nature of this combinational circuit. Truth table means it tells us the truth about the circuit. A table that tells us the truth about the circuit, what it does, how it does, what input gives what output, the true nature of the circuit. That is what the truth table reveals. Okay. For a Boolean function of n inputs, for a Boolean function of n inputs, there are 2 to the power n possible input combinations. for a Boolean function of n inputs, there are 2 to the power n possible input combinations. So here we have like 1, 2 and 3 inputs. For 3 inputs, we have 2 to the power 3. 2 to the power 3 is 8. So for a Boolean function of n inputs, so for a Boolean function of 3 inputs, there are 2 to the power n means 2 to the power 3, which is 8 possible input combinations. That is what we see here. 8 possible input combinations. Each row of the truth table lists one input combination. So each row will list one input combination and its corresponding output. Okay. So there are always 2 to the power n rows. Okay. The output column shows what the output should be for each input value. Okay. So now you understand. The above truth table is for 3 input, 1 output function. So there's a 3 inputs and 1 output. Okay. It has 8 rows for 8 possible input combinations and 1 output column. There are 4 input combinations where the output is 1 and 4 where output is 0. In 4 cases, output is 0. Okay, in 4 combinations, output is 0, and in 4 combinations, okay, if you see, the output is 1. Okay, so we have to write a find out basically in which cases output is 1. We have to write the logic, and based on that, we will say output equal to this or this and this something something. Okay. So what we will do is we will make K maps, Carnot maps, so which will give us better idea about how to solve this circuit. Okay. Uh, First delete this and then what we will do is we will say we will learn how to write a Carnot map. Okay. So what we need to do here is we need to make a map. We need to make a map like this, and we will write here x3, x2, x1. Okay, x3, x2, x1. So here we will write all the values for 0. So x3 0 means this first 4. So it's like 0 0 0 0 0 1 0 1 0 0 1 1. All these 4 we will write here, and after that 1 0 0 1 0 1 1 1 0 and 1 1 1. All these we will write here. So we write these as 0 1 2 3 4 5 6 and 7. So why we write this way is x2 and x1 combinations should be, you know, 1 minute. It's not responding for some reason. Wait a minute. This is not responding for some reason. Uh, okay. Let me see. Okay, great. Now it responds. So what we will do is, no, it's not. It's not properly helping today. It's creating issues. So this is the last problem we will solve. we'll need to see why this issue is happening. It should work properly. Uh, It should work properly. For some reason, it's not responding. It's a very annoying thing, but let it be. So we will do for 0, 0, 0. So what we will do here is we will write okay, 0. Please bear with me. Okay, 0 and 1, and then we will write here 1, 1, 1, 1, and then here we will write as 1, 0. Okay, so I'll try one more time if this works. Let me see. Great. So here we have 0, 0, 0, 1, 1, 1, and 1, 0. So we don't write 0, 0, 0, 1 and then 1, 0 here. Okay, we write 1, 0 on the farthest because we only want a 1 bit change here. It's like 0, 0, 0, 1. We only have this bit changing. From 0, 1 to 1, 1, we only have this bit changing. From 1, 1 to 1, 0, we only have this bit changing. If I write 0, 1 and then 1, 0, we have 2 bits changing. Okay, so we don't want that. This is called gray code. So when there's only 1 bit changing, if we group them, it creates a combinational logic in that sense that okay, if these two are combined, then we know x3 is 0, x2 is changing, okay, 0 and 1, and x1 is 1. So we can say we are including both cases for x2. So it's like x3 bar, x2 bar, and x1 plus x3 bar, x2, and x1. So it's like x3 is 0, x2 is 0, and x1 is 1, and x3 is 0, x2 is 1, and x1 is 1. You're getting it, right? So here we are saying x3 is 0, x2 is 0, x1 is 1, and here we are saying x3 is 0, x2 is 1, okay, and x1 is 1. So we are adding this, then we just get rid of x2 because it's like x3 bar and x1. Okay, because when we add, we get both possible combinations of x2. So x2 bar, which is let's say 0, and x2, which is let's say 1, because whatever is x2 bar, x2 will have opposite value. So if I add them, it becomes 1 only. So it's like if I add these two, what we do is, uh, let's say we don't write it this way. We write x3 bar. We take the common terms out. We write x2 bar plus x2 and x1. Got it, right? We x2 and x3 bar we are taking common, and this is what we are adding. If this is 0, this will surely be 1. If this is 1, then this will be 0. So if I add 0 plus 1 or 1 plus 0, in both cases we get 1. So this gets reduced to this gets reduced to 1. Okay. So we have x3 bar into 1 into x1, which is equal to x3 bar x1. So that is why we actually do this kind of setting, that 0, 1 and 1, 1. If I don't do that, what will happen is we will be trying to add x3 bar, which is 0, and then if this is 0 1 and 1 0, we will be trying to add x2 bar x1 plus x3 bar x2 x1 bar, which will be like x3. I mean, we can't make it common. If we do, we will write it in this way: x2 XOR x1. So this is a actually forceful way to combine. It doesn't become 1 or 0 this way. So to, it doesn't reduce like x2 bar plus x2. It doesn't reduce to 1. This reduction doesn't happen. It remains as it is. Okay. So let 1 minute. Okay. Let me make the K map again to explain you better. So we have this K map. We have we have x3, we have x2, x2 and x1, 0 0 0 1 1 1 1 0, and we have here 0 and 1. It's like 0 1 2 3. If you see 0 1 0, which is 2, and 0 1 1, which is 3. Okay, and then 4 5 6 7. Okay, what we will write here is like 0 1 2 3, 0 0 1 2 3, which is like 0 0 1 1, and then 0 1 0 1, 0 1 0 1. Okay, 4 5 6 7, 4 5 6 7. Then we will group it in this way. Okay, we have to find the minimum smallest group basically. So we will group it in this way. So what happens is this is x3 bar, and then what we have common is basically these two, like this 2, which is x2, plus for this what we have is x3, and then we have x1, which is common, x1. Okay, x3 bar x2 and x3 x1. So that is what we have to do here. Anyways, this will be the output. Out equal to, this is the output. Okay, the above truth table is for a 3 input 1 output function. 3 input 1 output. It has 8 rows for 8 possible input and 1 output column. There are 4 input which has output as 1 and 4 where the output is 0. Synthesizing a circuit from a truth table. So how to synthesize a circuit from a truth table? Suppose we want to build the above circuit. Okay, good. Suppose we want to build the above circuit, but we are limited to using only only the set of standard logic gate. How would you build arbitrary logic functions expressed as truth table? One simple method is to create a circuit that implements the truth table's function is to express the function in sum of products form. Sum of products means using a n-bit AND gate direct, okay, followed by OR that chooses only this. Okay. Okay. What it is saying is do it directly rather than doing some kind of reductions, doing it directly. So they are saying sum of product. So what we will do is, let's say we have uh, 3 inputs. We will do some AND operation. Then we have some more 3 inputs. We will do some AND operation. Then we have 3 inputs. We will do some AND operation. Then we have 3 more input. There are 4 outputs, which is 1. And then use this kind of a circuit to create, uh, you know, 4 input OR gate. Okay, very bad drawing actually. This is AND gate. These are all AND gates. Okay, these are all AND gates, and here we will have OR gates. Okay, this is OR gate. So this is how they are asking to implement. We will implement in both the ways. Okay, what we will do here is we will first implement it in this way. I mean this way, and then we will implement it in this way. Both should work. Okay, we will show both the outputs. We will say assign. Okay, let me take 4 wires then. Wire N1, N2, N3, N4, and then assign N1 equal to, what we will do is whenever it is 1 we will take these. So it's a x3 bar, x2, x1 bar, x3 bar, x2, x3 bar, not of x3 and x2 and x1. It's like not of x1. Okay, okay. So what we will do here is to just remove these things. We'll make a copy of this, multiple copies basically, in 1, N2, N3, N4. Okay, just trying to make our work easy. Assign or f equal to n1 or n2 or n3 or n4. Okay, so this will be our output, but then we have to rectify this logic. So what we have here is, first one is 0 1 0. So wherever we have a 0 we will put a NOT gate. 0 1 0. Okay, we'll just copy this. Then we have 0 1 1. We have 0 0 1 1. First was 0 1 0. Then we have 0 1 1. Then we have 1 0 1. We have 1 0 1, and then we have 1 1 1. Here we have 1 1 1, 1 0 1, 1 1 1. Okay, so yeah, let's submit and see uh, the answer. Okay, I hope yeah, x3 x2 x1. Yeah, correct. So yeah, it's a success. Uh, the way they asked us to solve, so that is how we solved. But now we will solve it in the shortcut way, because we have solved using K-map. Let's solve it in this way as well. What we need to do is, we don't need any wire. We will directly do and or. So all those things we will do. Assign f equal to x3 bar, like not of x3 and x2. So here we see not of x3 and x2. Okay, plus x3 x1, which is OR actually, or x3, sorry, and x1. Okay, so it's like not of x3, complement of x3 and x2. So you can see here not of x3 and x2, or x3 and x1, x3 and x1. So it will also give the same output. Okay, so Let me run it. Now it's running again. Okay, now it's running again. And now if you see, it's a success again. So it's the same circuit, even if we minimize using a Carnot map. Even if we minimize this truth table using a Carnot map. Okay. So now as let me check whether my this is working. So as this is working, we can cover more things. Okay. Uh, we can actually cover more problems here. Okay. So taken from 2015 midterm question, create a circuit that has two inputs A and B. So we have circuit that has two inputs A and B and produces an output Z. I'll try to continue this for about 1 more hour or maybe half an hour or 40 minutes and then we will stop. Okay, we'll try. Let me see what how much questions I can cover here. So create a circuit that has two inputs. So there's a circuit which has like two inputs A and B and produces output Z. Produces an output Z. The value of Z should be 1 if A equal to B. The value of Z should be 1 if A equal to B. Otherwise Z should be 0. So A is a 2-bit input, B is a 2-bit input, Z is an output. The value of Z should be 1 if A equal to B. Otherwise it should be 0. So we know of ternary operators. So what we will do is we will say assign. Okay. Z equal to, then we will write a condition and then we will write 1 if the condition is true. What is the condition? If A equal to B, A equal to B, Z should be 1 if A equal to B. Okay, so write the condition here that if A equal to B, yes, true means output is 1, otherwise output is 0. So how can Z get output 1? 1 means a 32-bit value 1. So we will write 1 tick B1. Okay, otherwise we give 1 tick B0. Okay, so yeah, it's a pretty easy problem. If our syntax is correct, yes, we have a semicolon and all. So yeah, it's a success as usual. Very easy problem. Let's move on to the next problem. Okay. So it says a simple circuit, so it will be simple. Module A is supposed to implement the function this and Z. Implement this module. So how to implement? Nothing. Just copy and paste. Assign. Simple. It gave, okay, implement this Z equal to X XOR Y and X. Very simple, right? Yeah, submit. Success. I didn't even implemented the code. They gave the code. I just copy pasted. It says like X XOR Y and X. That should be the value of Z. Simple. Let's move on to the next simple circuit B. Okay. I hope this will also be simple. Circuit B can be described by the following waveform. Okay, good. Now Z should be 1 when X is 0, Y is 0. Okay. When X is 0, Y is 0. And 1 when X is 1, Y is 1. What we will do is assign Z equal to when x is 0, y is 0. Okay, so it's like not of x and not of y. Okay, not of x and not of y, or okay, x and y. What it says is when x and y both are zeros, so not of x and not of y, or when x and y both are 1, x and y. Okay, so it's like x bar y bar plus xy. Can you tell me what is the circuit? So it says z equal to x bar y bar plus xy. So what is z is x nor y. Okay, or we can say x XOR y whole bar. Okay, so this is the actual circuit, but we are writing here what it is said directly. I'm writing here, and then we will submit. Okay, and it will be a success for sure. Let it cover. Yeah, it's a success. Okay, great. Now we will do this x XOR y whole bar or x nor y. So how to write x nor y is we will write not of x XOR y. I mean, this is one way. There are multiple ways. X XOR y whole bar. Okay. So let's submit it. Now we are submitting it again. See, we are running it again. Okay. Now see, this is also success. Another way to write x nor is x. No, this symbol not of XOR. Not of XOR is also called as x nor. So there's a success. I will run it again. See, now I am running it again. Okay. So see, this time also it is a success. So that means x nor can also be written as not of XOR. Okay, this is called x nor operation. But the best way to do is just write x XOR y and then write a bar or complement here. Okay, complement or not, basically not operation or bar operation. Okay. Okay, so let's move on to the next problem. Combinational circuits A and B. So they are asking for it seems multiplexers or something. See this and this for the sub modules used here. The top level design consists of two instantiations each of subcircuits A and B. So A have two instantiations A and here IA1 and IA2. B have two instantiations IB1 and IB2. Okay, we have input X and Y and Z. I don't know what they want us to do. X, Y, and Z is given. I don't know what they are asking us to do. So it would be for the submodules used here. Question 4A and question 4B. Okay. Implement this circuit. You have to see this simple circuit A and B. Okay. You have to implement this circuit. Okay. So what we have to do is simple circuit A and simple circuit B, we have to take into consideration. This is the A output. Okay, let's look at this problem later because I am continuously like solving problems for almost more than 1 hour. My ears are aching with this headphone and all. Okay, let me take a break, and after some time, because it's like we have to take this circuit output into consideration, circuit A and then circuit B. Circuit A is this, so circuit B will be uh, X naught. We have to take those into consideration and then uh, make this circuit basically. Okay, so we will slowly do this properly. Okay, in the next video. Okay, so 1 minute. So yeah, let us see this problem in the next video. And if you have any doubts in any of the problems before, if you haven't understood something, please feel free to let me know in the comment section. Okay. There's an alarm ringing here. Okay. So if you have any doubts, please let me know in the comment section. Uh, if the doubt is very easy to explain in a comment in the comments, I'll explain it in the comments. Otherwise, I'll make a separate video of it. Uh, if someone in the community can clear the doubt, that will be great. Otherwise, I'll be there to help you out. And as always, try to solve these problems first before looking at my solution or walkthrough. Okay. And if you have a different approach of solving this problem or any other things, please feel free to drop that down in the comment section. Write it down. So other people will also be knowing your approach, your way of solving the problem. Okay. And I'm always interested in discussing different implementation styles. So your inputs are always encouraged. Okay. So let's continue with this problem in the next video. Okay. See you all there. Bye.